So we can continue from the last session. So everybody is clear what to do for the design of desalination plant, assignment 3. So let's go a little bit more specific so you can have a better understanding how to design a desalination plant. So this is the flow diagram, how you can design your desalination plant. So how the seawater is flowing to your plant. And first, you have to go through chlorination and ferric chloride coagulation process, pH adjustment, dual media filtration. Here, you can change to the ultrafiltration. So you can design either dual media filter or ultrafiltration in this space. After that, you have to put the anti-scalant. So you have a lot of concentrate the salt. So this salt will clog the membrane and crystallize. So you create your membrane problem. So you can see the membrane crystal and then flux will decrease a lot. So how you can make this inorganic scaling problem. So anti-scalant can make the flow of the even high recovery or high concentration of salt. And dechlorination. So initially we chlorinated and dechlorinated again. What happened is the chlorination avoid your biofouling. There are many different microorganisms coming through your water. So if you don't put the chlorination, so your bacteria will grow in the pumps, pipeline, even the sand filtration, dual media filtration, they will grow slowly on the filters. So it's clogged again. So that you need to chlorinate to make sure that your infrastructure is very well maintained. After that, the reverse osmosis is a polymer. So this is a polymer. So if chlorine is passing through this membrane, so this membrane is a polymer, so oxidized. So your oxidation will damage your polymer membrane. It's like a plastic membrane. So we want to dechlorinate it. So remove the chlorination and oxidant. That's the reason you can have a more long-term operation of a reverse osmosis membrane. After that, permeate flowing post-treatment with lime and fluoride, chlorination again, and supply it to water distribution. So this is the flow diagram. So we can discuss about one by one. So how much chlorine you have to put, and ferric chloride as a coagulant was removed some organics or some of the large particle, and then pH adjustment. So what's the pH of seawater? What's your pH of the drinking water, tap water? Sorry? 6 to 7. So neutral pH, right? That's correct. So what's the seawater pH? Higher. 8? Yes, you're right. 8. So pH 8. So seawater is higher pH, and you are drinking the neutral pH. How about Coca-Cola? What's the pH of Coca-Cola? Higher pH. Huh? 3 to 4. So Coca-Cola pH is 2. So you're drinking the Coca-Cola pH 2. How about milk? What's the pH of the milk? Neutral. Eh? Is it from AI or from your opinion? Yeah? Google, right? Yes. So we have a lot of different pH we are drinking, like Coca-Cola pH 2, lemonade also pH 2. So when you enjoy your barbecue, so people like to drink the Coca-Cola because pH 2 will clean up your oily, yeah, inside. So remove all the oil inside your, yeah, intestine. And we have also neutral pH, drinking water, and pH is high. So which means the OH alkalinity is a higher concentration inside the seawater. And this will create the scaling. So calcium hydroxide, magnesium hydroxide, iron hydroxide can be easily combined and then create the scaling, like the inorganic scaling. So we need to decrease the pH from 8 to 6 to make sure that no scaling occur in the process, in the pumps, pipeline, membrane, everywhere. So decrease the pH to 6 and dual media filtration, anti-scalant. So we can have a more different chemical involved. So you can calculate. So you need how much chemical you have to incorporate inside your water. So you can easily design the chemical demand, how much it will cost. So easily you can calculate. So let's see the one by one more detail. So let's just see mm, organic carbon. So seawater originally pH is 8, right? So if you look at the dissolved carbon, so CO2, a lot of people are now talking about decarbonization. So inside the air, so we have a CO2 concentration. So this CO2 is dissolved in seawater. So depending on the pH, this CO2 can be changed to so when you have a pH 8 seawater, you have almost bicarbonate HCO3 minus. So you have a more higher concentration. That's the reason why the pH is around 8 because seawater contain more bicarbonate. So this bicarbonate can easily produce our lobster or oyster or crabs. So if you see this kind of seawater animal, So they have a very strong skin, right? So this is the calcium carbonate. So seawater, you have a pH 8. The CO2 dissolve from the air to the seawater and convert it to the bicarbonate, HCO3. And animal can capture this concentration and combine with the calcium, and they produce the very strong skin of a lobster or oyster. So that's the how we would have a climate impact. Like if you have a concentration is higher, yeah, then pH change. So when you change the pH, and then this kind of animal cannot create their skin, and you cannot create the calcium carbonate. So that's the also impacted. So pH, when you have a pH 6, also you have this HCO3 bicarbonate, but the pH more than 8.5, so you will have a carbonate concentration. So you will get this, and then CO2, when you have a pH less than 4, so CO2 just dissolve directly in seawater. But the CO2 itself cannot really dissolve because the seawater is a pH 8. So you can see the CO2 itself converted to the bicarbonate or the carbonate compound. So this make easily you can have a better way of the animal calcium carbonate production. So this one, the reason why the pH seawater is basic between 7 to 8. At this level, pH carbonate is bicarbonate is predominant, and that's the reason why the pH is more about this 8 condition. The carbonate ion concentration increase with increasing pH. When the more CO2 dissolve in seawater, it becomes more acidic. So when you have a more acidic condition of seawater, so this will damage a lot of ecosystem of seawater. So that's the how the bicarbonate carbonate affect the overall pH and pretreatment. So conventional dual media filtration, ultrafiltration. So ultrafiltration membrane is like this. So some of them are hollow fiber, some of them are plastic. So you can have this ultrafiltration, which you will up to the ultra pore, which means around 0.02 micrometer pore size. We have a very small water molecule ion, or talking about the larger particles stay behind the infiltration. So you have a easily connected with space. Your fiber, so you have pore here. So you just suck this water, then water will flow inside a hollow fiber. And you collect the filtrated water. So this is the pre-treatment because you remove all the large particles, only dissolve the ions will pass through this pre-treatment membrane. So compared to the sand filtration, sand is the largest size. So you're packing the sand. There's still a lot of small particles could pass through your media filter. But the ultrafiltration membrane, you can remove the most of the particles so that you will have a better quality of your treatment. So, like previously, a lot of people utilize the pure media filters because it's a very cost effective and then very much easy to operate. But nowadays, the advanced ultrafiltration membrane can have a pretreatment to get the better quality of reverse osmosis membrane. So you have a more filtration, you can get the more sustainable RO membrane operation. So ultrafiltration and this media filtration has a different cost. It's very much similar. Ultrafiltration is a little bit expensive, but very similar price. So people select ultrafiltration as a pretreatment for this process. So anti-scalant. So if you see the anti-scalant, calcium carbonate, so you remove the water, desalinate, and then your concentration of salt, calcium bicarbonate or carbonate keep increasing, and then they are continuously concentrate on the membrane surface. Yeah. So calcium carbonate, as you can be seen, they have a scaling and then clog your membrane, so water cannot pass through. Also, calcium sulfate in the middle. So calcium sulfate, we have this kind of inorganic scaling you create. Also magnesium carbonate. So carbonate, seawater contain very high concentration because of CO2 relationship. So we have a more CO2 increase and then dissolve the more inside your seawater, and they have also more creating the problem for this inorganic scaling. So anti-scalant are surface active. So we need to put the anti-scalant. So how we can remove this kind of scaling? So we can incorporate SHMP. So this is the anti-scalant. It's kind of a sodium phosphate uh, compound. So this sodium phosphate, before calcium and carbonate attached together, combined together, so they are interfering like sodium hexaphosphate interfere together and then reduce the overall scaling and then crystal growth. So that's the anti-scalant. So when you design your seawater desalination, so depending on your recovery, depending on your process design, so you will have a warning sign in your software. So in this case, you need to put this anti-scalant to reduce the overall the scaling issue in the reverse osmosis membrane. Also, dechlorination. As I mentioned, initially we chlorinate it to protect our process. And then before reverse osmosis, so we dechlorinate. So how we can dechlorinate? We're using this sodium meta bisulfite. So sodium meta bisulfite dosing rate is 3:1 ratio. So chlorine is an active oxidant. So how we can put this SBS, chlorine, and then they react and produce the sodium HSO4, and then you have HCl, so that the chlorine easily converted to the ion, chloride ion. So you can protect your RO membrane, otherwise the chlorine will oxidize your membrane, which will damage your membrane. So that's the also another strategy, activate carbon filter chemisorption process where the chlorine reacts with the carbon sulfate. So chlorine gas converted to the chloride ion, which can make more less oxidative. So that's the how we can make a dechlorination. So you can also design chlorination, dechlorination, put the SBS with 3:1 ratio. We'll have a good dechlorination performance. Also, remineralization. So after RO permeate, the water is very clean. It's like a rainwater. So people don't drink rainwater, right? Also, we don't really have a rainwater quality from the tap water. So it's land to the rainwater is just pass through the river and then groundwater, and they absorb the mineral like sodium, calcium, magnesium from the our soil or from the our different nature. So mineral is dissolved in the rainwater, and then you just collect in the reservoir. So the rainwater, even though its source is from rainwater, but they are continuously mixed with mineral in the dams, and then we get the tap water. So mineral, rainwater. So rainwater itself, it's no buffer solution, no mineral. So this is not a good water source, even though it's clean. Sometimes too clean is not good enough to drink because nobody drinks the distilled water, nobody drinks the rainwater because of they are easily contaminated, easily change the pH, also make your pipeline very corrosive. So pure water is not always good for the drinking. So you have to put a little bit of buffer solution inside the water, a little bit of mineral. So we need to have a remineralization after permeate because sodium, every mineral remove, and then you have a very high purity of water. So mineral is not good enough. So remineralization has this kind of adverse effects, high corrosive potential, and then dietary deficiency causing risk of this heart disease. And then we need to put some of the calcium or magnesium, different mineral. So WHO recommend 10 milligram of magnesium, 30 milligram per liter of calcium. The calcium, magnesium are very good source of our nutrient and good mineral functioning our metabolite more active. So people put some of the calcium and magnesium inside, and then you can have a better quality of demineralization. So two solutions are widely used to mineralize the water. So calcium CO2 addition. So you can put the CO2, produce the carbonate, bicarbonate. So you have a pH 2. So CO2 converted to the bicarbonate, and then they have like a buffer solution function. And the CO2 also created a good quality of your sources of the water. And calcite, limestone, so calcium carbonate. Calcium carbonate has very good also our mineral and magnesium oxide and sodium carbonate. We can have this uh, remineralization, also calcium chloride, sodium bicarbonate. We can incorporate to have a better quality of our drinking water. So remineralization will give you better way of your drinking was very much secure to transfer to the pipeline. That's the reason why they put also chloride is just cavity purpose, and then we are producing this kind of desalinated water to drink. And this is the annual and operation cost. Mostly desalination need energy. So from the last session video, Do you remember the wind farm? Yep. The city desalination plant, the energy source is from the wind farm, renewable energy. So they produce the electricity uh, and then supply from wind energy. So it's more about the renewable energy. But still, energy cost is very, very high, more than 50% in desalination. So if you think about the energy cost, how to save in the desalination plant, also you can contribute a lot of overall economics for the seawater desalination. And we have chemicals, membrane replacement. The membrane can be replaced. How long it lasts for the membrane from the seawater desalination? Around, some of them are 1 year, some of them are 3 years, depending on the initial stage of the membrane. Yeah, observe the more foulant, so they have a more replacement frequency to make sure that the sustainable flux. But at the end of your module, so you don't have much fouling, so 3 to 5 years. So in average, you have this 3 years, 5 years. So how much it costs for this membrane element? We just say element. How much it costs for this element? It's around $500, 600. This is around $500, $600. So they can sustain 3 to 5 years and produce a lot of water. You can also, how many elements you need? So that's your assignment. How many elements? This is, let's say, $500. So you need to design 250 megaliter per day. So how many elements you need, which costs around $500? Around, yes, it's around, you need to have this one more than 50,000 elements. So it shows a lot of capital cost. You have to incorporate also replacement every year. So maintenance, labor cost, indirect cost. So energy is the target for seawater desalination. That's the reason why not only Sydney desal plant, every desal plant in Australia operated by a wind farm, because they like to have more renewable energy because of energy very much required for desalination plant. So we have to think about how we can save this energy. It's one of the future research area for seawater desalination. We need to learn a little bit of terminology for designing the flux. So already you may have experienced this flux-related terminology throughout the per membrane. So you have a 1 meter, 1 meter, 1 meter membrane. Yeah. So you push it through water, then permeate is coming. So 1 square meter membrane surface, how much time you pressurize and how much water is produced. Let's say this is the one element. One element contains around 40 to 50 square meter of membrane surface area. So 50 square meter membrane we have. So I push it through 1 hour. So how much water is produced. So you can design your, what's the surface area membrane? Okay, you pressurize for 1 hour how much the water is desalinated. You can calculate one element. Okay, we can produce the, let's say, 3 LMH, 3 LMH. So 1 square meter, 1 hour. Normally we design the 20 to 30 LMH. So which means this one element multiplied by 50 by 520. So 1,000 liter. So one element, 50 square meter. For 1 hour, this element produce 1,000 liter. So 1,000 liter, how much it cost? 1 cubic meter is around $2.3 in Sydney water, tap water. So in seawater desalination, so 1,000 liter for 1 hour from this module. So they produce, what's the cost of the overall membrane desalination? So you can also calculate how much is required for the flux, water, and how this will reflect your overall drinking water price. So you can also calculate the overall this kind of energy and then economics. And permeate, the water treated by membrane, permeate often called filtrate, microporous application, permeate common in RO and F, sometimes ultrafiltration. So we just say permeate, pure water passing through membrane, we just say permeate. Feed water, permeate, after you permeate, so you have concentrate brine. So we have 3 different feed water, permeate, and concentrate. So you can also utilize the this terminology, and concentrate is concentrate waste from membrane. So recovery is very important. So seawater, we have a 3.5% of salt is coming. Then let's say we have a recovery 50%. So permeate is 50%, brine is 50%. So our recovery, permeate and feed side, feed was 100 and permeate is 50. So we could say 50% of recovery. So recovery is very important because when you have a higher recovery, higher, so your final brine concentration of salt is very high. So you create the calcium carbonate, calcium sulfate, a lot of inorganic scaling crystallized so that the membrane is damaged. So recovery in your assignment, in general, seawater, we design 40 to 45%. So if you go for more than 50%, you will have a lot of inorganic scaling in the membrane element. So 40 to 45% recovery, you can design for your seawater desalination. TMP is the transmembrane pressure, and transmission is the passage of certain solute across membrane. Opposite of rejection, transmission is 1 minus rejection. The unit is also important concept when you design. We just say unit or train. So we want to design 250 megaliter per day. So when you design your process, you just separate smaller size. So 250 megaliter. So you don't design at the same time 250 whole water. We separate okay, I want to design 50 megaliter per day as a one unit or 10 megaliter per day, one unit. So you can make a 10 megaliter per day, one unit, several unit will make a 250 megaliter. So one unit, you can make a smaller size because this one unit provide one pump and then module and energy recovery together. So you can have a easy to separate just in case you have some faulty operation. So you still have a different unit is keep reducing water, even when you have a maintenance stop or cleaning. So you can start the one unit and then operate other unit. So you can have a one unit design multiply by your final products. Yeah. So final product can be designed by smaller your unit. So one unit is a grouping of membrane vessels with common feed pump, piping, and control system. Element, so this is element. Individual membrane unit is one element. And then module is ultrafiltration, microfiltration, cassette, CIP. CIP is cleaning. So when you apply 1 day, 2 days, so you have a more organic is attached on the membrane or some inorganic scaling. So you need to clean up, acidic cleaning, base cleaning, or some flush the water will give a good cleaning to produce the more water flux. Backwashing, intermittent reverse flow to remove solid. Also, enhanced backwash is reverse flow with the brief chemical loading used to increasing CIP interval and chemical enhanced backwash, enhanced flux maintenance. So when you have this ultrafiltration membrane, so you continuously pressurize, and then your organics or particles continuously accumulate on the surface. So sometimes you have to backwash, okay, backwash, and then they detach, and then you can easily remove the foulant. Also, you can have sometimes chemical cleaning to remove your membrane surface, all the contaminant. So that's the how this can make a good backwashing cleaning for ultrafiltration membrane, reverse osmosis membrane. So water quality parameters. So what's the seawater inside? So what water quality will impact your design? So you want to design how many elements, how many vessels, how many pumps, how many pressure, energy recovery. So you need to look at the water quality. And then this will give you how much module we need, how many elements we need, how many pressure vessels we need, how many banks we need. So this is the impact our overall design. So water quality is the first step. So you need to look at the turbidity. The high turbidity is always make a lot of membrane fouling, remove the, so that's why we need to remove turbidity using ultrafiltration membrane or dual media filtration. This will give a good quality of grade to RO. So they will have a less turbidity, and then RO has a very small space. So you can see the space. One is the spacer, and we have a membrane, and we have a back spacer, permeate spacer. So the channel space is almost a millimeter, 1 millimeter. So water is passed through this way. And if you have a lot of turbidity, you're clogged here. So making sure your turbidity is completely removed, and then you can see how we can protect this membrane. And total organic carbon and SDI, total suspended solid, iron, manganese, silica, chlorine, temperature, oil, grease, pH. So they all affect your design of your outer membrane. Because it's a water-related viscosity change, density change, water flowing change. For example, let's say, so you're operating your outer membrane in winter time. So seawater temperature, what's the seawater temperature in winter? Around, let's say, 10 degrees, right? How about summer? Let's say 30 degrees. So you have a temperature difference. 10-degree winter time, you have to operate seawater desalination. Summertime, 30 degree. So depending on your temperature, so water density change. So seawater water density of winter time and summertime. So which density is higher and then which density is lower? So winter 10 degree of water and 30 degree of water. What's the water density difference? It's which one is lower and higher? So when you have a low temperature, water molecule is shrinking, right? So you're like you're very cold, you're shrinking. Same as water, yeah. They also shrink. Then summertime your temperature is higher, 30 degree. The water is a little bit relaxed. So density is mass to volume. So shrink is the more less volume. So which means same water but less volume. So density is higher, right? So cold water density is higher. Hot water 30 degree density is lower. And which water is pass through better? 10 degree or 30 degree? The high density, low density. So which water is easy to pass through your membrane? So low density is more difficult, but the high density is easier to. So high temperature is recommended for your higher flux. So 1 degree will change your water flux 2%. So 10 degree is almost 10%. So when you operate the winter time, your flux is maybe 10 to 20% lower than summertime. So when you design, okay, you have to design 4 seasons, summer, winter, autumn. So we have to make average temperature rather than summertime design, winter time is the less workable. So you can make it sure when you design, okay, we want to design 20 degree of average water flow. So this can have more buffer. Your winter time, summertime, you will have a good flux, even 4 seasons. So that's one of the example. Temperature, also viscosity. Low temperature has higher viscosity. So if you just put your water drops, for example, you have mm, two water drops. One is the 10-degree water, 30-degree water drop. So you just make it slow. Then let it flow. So which one is flowing better? Low temperature or higher temperature water? If they're going faster, flowing faster. The viscosity will affect this kind of water quality. The low temperature, more viscosity. So it will be slowly going down. But high temperature, less viscosity, so they are faster. The same as water density, water viscosity, even membrane form, they easily possible or difficult possible for viscosity and density. The temperature also affect overall your water flow. Other compounds are more about scaling and fouling issue. So you have a high concentration, then you can get the more clogging of the your membrane. Also carbonate, carbon dioxide, its buffering capacity, acidity, and alkalinity, hardness, phosphorus, and TDS, osmotic pressure. Second important, not second, this is the most important, your design parameters. Osmotic pressure. Osmotic pressure. What's the osmotic pressure? So we just say this is reverse osmosis. The meaning of the reverse osmosis is reverse. Opposite is forward osmosis. So let's think about osmosis. You have a high concentration of salt. So this has a chemical potential. Yeah. And this converted to the osmosis. So you have two waters. One is the no salt. Yeah. You have a seawater here, rainwater and seawater. The volume is the same. However, this seawater, 3.5% of salt, even though you cannot see inside, you cannot see the sodium, chloride, any of the ion inside, but it's completely dissolved. So it's completely dissolved, and then they have chemical potential, which called osmosis. So what this osmosis is doing, it's doing the problem of our separation. The water molecule is very small. Sodium is a little bit larger. Now we need to separate these two molecules. And then what happens when you have a higher concentration of sodium and water, they try to continuously attract each other because pure water like to combine with a lot of salty water. And then salty water also diffuse to your pure water. So this is the kind of your uh, attraction in your seawater. So you want to separate. So when you separate this one, so you are using membrane. The reverse osmosis membrane will look at the higher concentration, your chemical potential is higher, and then you have a osmotic pressure. So this osmotic pressure will design how much pressure we have to apply. to detach your water molecule and then your salt, and then water molecule only can pass through. So pure water and the salty water has a different concentration. So we just say this is the osmotic pressure difference. So if you have a higher concentration of salt, you need more pressure to separate your water molecule. You have less TDS, you have a less osmotic pressure, so you have a less pressure applied for your reverse osmosis. So osmosis, what's your blood pressure? What's your blood pressure? Blood pressure. Okay. 70 to 100. So we have a pressure in our body, blood pressure. So this blood pressure is keep circulating in our body. So if you see the blood inside, what's the salt concentration? Osmosis. It's like a osmosis. Can you observe your nutrient from your stomach or small intestine, large intestine? Yeah. So your blood has to have a energy to suck your nutrient, right? So your blood pressure, salt concentration is almost 0.9%. 0.9%. So you have a 0.9% of salt inside, a lot of nutrient, a lot of hemoglobin or red cell. There are many different dissolved solid inside your blood, right? So this 0.9% creates your pressure, blood pressure, and then keep sucking your nutrient in your bloodstream, supply to your hair, supply to your feet, everywhere in our body. So this is osmosis. Okay, our body is like osmosis because of concentration difference. We have membrane. Our skin is membrane. Your stomach is membrane. Your blood is everywhere, like your kidney membrane. It's like a membrane. So you can see that one of the examples. So you have exercise. So you're sweating. So where is this water from? From your body. So it's like a membrane. They keep pushing out your water molecule because your body is getting hot. Outside is cold. So you push it, your water molecule from your body to outside, and then you're sweating. And then this is membrane, right? Also, when you think about shower, so when you take a shower, yeah, when you take a 1 minute shower, your body is okay, your skin is okay. But when you take a shower 1 hour, what happened? Yes, your skin is swollen, right? Because your body has osmotic, high concentration of your salt. And then water molecule is keep penetrate your skin, and then your skin is keep swollen because of water is keep accumulated on your skin. Yeah, it's like osmosis. So this is natural, like the same as trees. There are many trees, many plants in Blue Mountain. So how they capture the water? Because of osmosis. Inside the tree, they have a higher concentration and the water molecule. They try to continuously passing through the osmotic power to absorb the water molecule, pure water molecule. So that's the osmosis. And reverse osmosis is we reverse way. We pressurize and then we change to the high salt to the low salt. Yeah, that's the what we like to do, reverse osmosis. So against the osmotic power, then what we need is a pressure. That's what it is. We need pressure to reverse osmosis. So membrane, we just say reverse osmosis can make this kind of. So if you have a higher concentration of total dissolved solid, osmotic is higher, then you need more pressure to separate your water molecule and sodium or other salt. If we have less salt inside, that's the reason why seawater desalination is a very, very energy intensive because pressure has to be 60 or 70 bar. It's like higher than this atmospheric pressure, let's say 1 AM, 1 bar in this condition. 60 times, 70 times, you have to pressurize and then you can separate water molecule and salt. That's the exactly, we need the energy to pressurize 60 bar every day to produce the water. So that's the reverse osmosis we need to thinking about. And then TDS, temperature, also some scaling, turbidity. So they are all important to design. However, for your assignment, already your water parameter is in your scenario appendix. So you can see the basic parameter from the appendix. Then you can utilize that and you can design a very typical way of, you don't have to worry about too much turbidity or too much different manganese or iron because you don't have a chemistry background. It's very difficult to calculate what's the calcium carbonate saturation point to create the membrane fouling, what's the manganese oxide, what's the different calcium phosphate, calcium sulfate, calcium carbonate, which concentration, which condition it will create. So this is a chemistry area so that if we utilize the wave software, there is a prediction of the you concentrate your seawater this much, then you will create the precipitation of calcium carbonate, calcium phosphate, or the different or inorganic scaling can be predicted from this software, and then you can just utilize it rather than you calculate water chemistry to see the inorganic fouling. So rest of them, we rely on software to see the detailed chemistry, precipitation, and the fouling issue. Only we like to focus more about temperature, I think physical, and also osmotic pressure, because we can easily calculate the recovery. So the seawater 3.5%, osmotic pressure is almost 28 bar. So 28 bar, I want to recover almost 50%. So osmotic pressure 2 times. So 7% of the concentrate. So pressure require around the 60 bar based on our osmotic pressure from the different salt concentration. Okay, so we need to pressurize 60 bar, 70 bar, depending on your recovery. So that's you need to calculate and then design. Also temperature, we just make a very average temperature. Look at your yearly seawater temperature here to here, and then how this can be better design. So that's the essential water quality parameters you can consider and design for your seawater desalination. But as I mentioned, this software will provide very good water chemistry, and then they will also guide you whether you need an anti-scalant, whether you need to change the pH. So you can see that tomorrow we will go through this one. If you put all the cationic, anionic, neutral ion, and turbidity, what's the turbidity after pretreatment? Potentially ultrafiltration. After that, because this is a RO design, so you don't have to put the initial seawater influent. You need to put the after pre-treated water turbidity and total suspense solid, SDI. SDI, I will talk tomorrow. SDI value, what's the temperature, pH? If you put this data as detailed as possible, and then you design recovery 50%, 40%, how this will concentrate, what's the overall concentration, inorganic scanning, prediction. So this software will tell you, or you have a inorganic classification, you have a problem of pH, decrease the pH, or they asking, oh, can you put some anti-scalant in your feed water, which will avoid your overall inorganic scaling. So this software tomorrow, we can go through one by one tomorrow. So you don't need a very strong chemistry background, just the basic concept and then design for your reverse osmosis membrane. So this is the web software, water quality parameters. You can utilize the software without any water chemistry background. And RO. So this is the most important technology we have to utilize for the water desalination, right? So let's go for a little bit RO fundamental. The history, 1956. The desalination history is maybe thousand years ago, right? Because the distillation already people maybe Middle East or some other than that. So they made the water, the potentially water is from seawater, they don't have enough river water or fresh water. So near around seawater, they may boil the water, then they realize, oh, we have distilled water. Oh, this is okay, great. So it happened maybe not favorable. So that's the first desalination history. But we are talking about RO. Distillation was very simple and very effective if you have enough energy. So when you have an oil price like that, now it's a company of the oil price to be happy. At the time, it was longer ago, they had a happen oil price. Oil price increased. At the time, they utilized the oil to oil the water. Oil price increased, and desalinated water suddenly 2 times, 3 times, water price increased very high. So they decide, oh, we need to look at the different way, otherwise oil cannot capture our drinking water. So they decide to develop new technology, reverse osmosis membrane. So this is operated by electricity rather than oil. So electricity, 1956, first desalination plant, Kuwait, and desalination commercial plant happened 1970. And At the time, distillation was still better than reverse osmosis initially. 10 kilowatt hour per cubic meter. Reverse osmosis has been dominated since 2000. It's almost 26 years ago. It's not too far. Before that, 2000, before 2000, oil price was still cheap. That's why people utilize the boiling, the distillation. The reverse osmosis was developed 1970. However, it was still expensive than distillation because it was not optimized, membrane was expensive, and nothing much developed at the time. But continuously they developed this membrane, and then 2000, one researcher developed pressure experiment. So we pressurized the RO 60, 70 bars. Before, they just wasted this pressure until they produced the food quality water. But 1997, one researcher developed pressure expander, like a heat expander. You have a hot water, after heat utilized, and then you have a heat expander, heat observer, and then your heat side. Same as the pressure exchanger was developed 1997. Then they say the overall energy consumption or reverse of that. Since then, 2000, they continuously grow reverse osmosis. Then now it every desalination plant, even Australian reverse osmosis is the dominant because compared to the boiling, much cheaper than for distillation process. And we had also some of the breakthrough for new membrane continuously developed. Then aerophotonic process would become many like material development and continuously improve the overall performance of the reverse osmosis. That's the reason why they have now seawater desalination 4 kilowatt hour per cubic meter of seawater desalination using seawater desalination. So nanofiltration, reverse osmosis. RO can remove most of atoms, metals, and nanofiltration was removed some of them, but reverse osmosis can remove very small molecule, sodium, chloride. Then how look like this arrow? So they are non-porous or porous. We just say microfiltration, ultrafiltration, even though you cannot see the pore from your naked eye, but if you use a microscope, see the very large, and then you can see the pore, okay, 0.2 micrometer. So you can see micrometer size, even nanometer size. But reverse osmosis, membrane, you cannot see pore, even though you look at the very detail. So just say non-porous membrane, even though you look at very, very big. So which means they have a different transport mechanism. Ultrafiltration, it's a size exclusion because they have a pore. The size is this big. Water molecule easy to pass through. Iron is easy to pass through. Some of the, it's completely depending on the size exclusion. So if you some material smaller than this pore, so you cannot pass through membrane. So just say size exclusion transport. But non-porous, it's not like a size. It's more about osmosis of separation transport phenomena. So membrane thickness increase, permeate flux increase, active layer is very thin, very, very thin. So you can see like this is outer membrane. It's like a paper. Yeah. Like a paper. But in this paper, we have 3 layers. One is the monogroup support layer. In the middle is the polysulfone polymer. On the top is the polyamide, it's a nylon. You have somebody has a nylon material. So this is like nylon on top. So nylon is very thin, like the 100 micrometer. Very thin. Then polysulfone is supporting this nylon. Then normal material is also supporting because they need to pressurize 70 bar. Temperature, so they have to tolerate this kind of very strong pressure condition. So it's this kind of outer membrane, so it has to be very thin because if it's too thick, water cannot pass through. It takes time. So they make it as thin as possible. So quickly let them pass through the water molecule. Then you have higher flux and membrane structure asymmetric. That's why we have a 3 layer. The bottom layer is very thick. Middle layer is middle thick. Then polymer of this outer membrane nylon is as thin as possible. So that's why we just say asymmetric membrane, composite membrane, and then this will separate your sodium, water, and desalinated your water. And let's say that this is module. Let's say exactly, we just say 1 element, yeah? And then see the membrane. So we have an ultra thin polysulfone backing layer. These 3 layers exactly happening. And then we can separate our water molecule from this membrane system. So it's like a 20 nanometer. Your nylon active layer on the top, it's a 20 nanometer of your thin. So it's very small. Then let's see how this membrane is manufactured and then fabricated.
To create our standard spiral wound membranes, we construct the flat sheet membrane using Hydronautics automated casting equipment. We begin the process with a fabric support base and then coat it with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water. The semi-permeable polyamide layer consists of a thin film of polymeric material, a few thousand angstroms thick, formed on a porous supporting material. Semi-permeable membrane skin is formed on the polysulfone substrate by interfacial polymerization of monomers containing amine and carboxylic acid chloride functional groups. Hydronautics manufacturing procedure enables independent optimization of the distinct properties of the membrane support and salt-rejecting skin. The combination of these three layers makes a durable membrane flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane surface. The leaves of membrane and feed channel spacer are then combined with a sheet of permeate spacer, which provides open flow channels for the permeate even under high pressure. The leaves are glued along each of the three exposed sides and then rolled around the core tube. With the back of the membrane completely sealed to the edges of the permeate spacer, the feed water is forced through the feed channel spacer, contacting the front or barrier layer of the membrane. Clean water, or permeate, passes through the membrane surface into the permeate channel and then flows in a spiral direction to the center of the element and is collected into the core tube. Hydronautic spiral wound elements can then be loaded into pressure vessels, interconnected with additional elements to complete any number of design specifications. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced and then treated. The feed water that does not permeate through the membrane becomes enriched in salts as it travels through the feed channel spacer due to permeate water being removed. Typically, 8 to 10% of the water is removed in one 40-inch long membrane element. The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed. Typically, 70 to 90% of the water can be recovered as pure product water.
So that's the polyamide material using artificial polymerization and make this membrane. Then they put the membrane and roll this spiral out element. So water traveling through this and come to this middle hollow area. Then you produce the pure water. Then concentrate water is passing through, continuously through this space of water. So this is the element. So you have to design this element, design the pressure vessel, design the one unit, and then finally you can design the sewer. That's how we have to do your assignment. Now it's you're getting familiar about what how this is traveling, how many elements you have to put in one pressure vessel. So how many pressure vessels you have to design, how many elements you have to allocate. So you have to look at the staging, past different skills you have to understand to design the seawater desalination, because one element will recover around 10%. Next element will recover around 7%, because concentration is keep increasing. Your feeder side, after passing through water, is pure water is continuously being discharged. And then your feed side is concentrate and then go next element. Your high concentration is less water flow and you have a less water recovery. Next element, another change of your feed concentration, water flux, recovery. So you have one pressure vessel. So you have inside 1, 2, 3, 4, 5, 6, 7 elements. Each element contribute different recovery, different water quality, different water concentrate and osmotic pressure, then we need to look at what's the best way to arrange this one and produce the 50% recovery of your water and water quality, and how we can avoid overall inorganic scaling. So when you have a high recovery, you have a more inorganic scaling. How this can be designed, that's exactly you have to think about for your assignment. So that's the reverse osmosis we are separating, and mass transfer phenomenon, like osmosis. Already I talked about our body osmosis everywhere. Kidney, yeah. Osmosis, our kidney is the most functioning our osmosis. So what's the lifetime of the kidney? Maybe 100 years. Even people may not die because of kidney failure. Okay, some people, yes, kidney failure is a problem. But let's think about kidney as an osmosis. So you eat the food on lunchtime. So you eat lunch now, yeah. Then this lunch has a nutrient, nitrogen, phosphorus, potassium, every nutrient going to the stomach. Yeah. So your stomach pH is 1.5. So stomach acid, like that. You produce a lot of acid in your stomach. Dissolve your all the food inside your stomach. And easily you dissolve your nutrient, nitrogen, phosphorus, potassium, and some carbohydrate. So they are all dissolved in the water. They're going to the next step. And your blood will continuously absorb nutrients like nitrogen, phosphorus, all the nutrients is flowing through your bloodstream to our brain, our heart, our feet, abdomen, keep supplying to the nutrient beyond the brain. And the last stage, they are going to kill it. What happens is kidney, okay, this bloodstream already they supply every nutrient, and they are already very well utilized. So you need to discharge, which is the bad cell, or you need to discharge unnecessary over nutrient. So you have a function of this kidney, and then this kidney will have a membrane. So this membrane will try to remove your unused nutrient or the dead cell, like dead cell, they will hemoglobin or different, it's not active wasting, has to be separated from the kidney and goes to the bladder and you urinate. So if you see the urine, your urine, what's the color of urine? Light yellow. So this yellow is from where? So sometimes you take a vitamin. The vitamin has that yellow color. I then get yellow because vitamin itself has a yellowish dye. But if we don't take a dye, as it is, you will see yellow, right? Because this yellow color is from your red cell. Either by red cell in the bloodstream, they have the diversion of very, very high and die. Then it comes to the body system and this change to the bacteria. And this blood is that continuously we remove our waste from the blood line in your kidney. So this kidney will continuously discharge for your urine, unnecessary, your blood nutrient, and then they can create the more healthy bloodstream for your body system. And the osmosis is just thinking about our kidney, our body, they are all functioning like osmotic power, osmotic energy. And then this will give our life concentration, polarization, permeate flux, and then we will continue this one. Now it's the 12:30, so we can have a lunch. Then we can continue after this lunchtime. 1 hour, 1:30, yeah? We come back to our class 1:30. Then we can continue to talking about more detail osmotic, because this will help you to design your overall reverse osmosis, pressure calculation, recovery calculation, concentrate calculation. So osmotic pressure, how we can calculate as a formula, and then how we can apply to our design of recovery and design of the overall concentration chain. So you can come back 1:30 and then we can continue with the detail of transport phenomena. Any questions so far? Any question? No? Okay, see you at 1:30.